Hi there. So what I thought I might do is just solve this problem just, off the top of my head, really. I mean, I did actually create this whole problem myself, so I'm kind of already aware of how the solution should run, but it was actually quite a while that I did it. So you'll probably see me sort of organically sort of figuring things out again as I go through the problem. That's not a bad thing, I don't think, but it might make this a little bit more organic or flexible as I sort of come across a solution. So let's see how we go. A startup company was given $1 million investment money. Its yearly capital, its net worth is modeled by this equation here. Okay, cool. Where C is the amount of money in millions. Okay, so when C equals 1, that would be the $1 million, etc., of capital that the company, and T is the time in years. Okay, cool. Since the initial investment. Okay, so you notice I'm just circling stuff that's important. So it's going to draw my eye back to the problem as I go along. At what rate, that's that key word there, rate. At what rate is the company's capital, that's C, changing at the time of the initial investment? So we know that initial means at the start. We know that rate is a rate of change, and therefore, gosh darn it, in a calculus section of a test, what does that mean? It's finding the derivative, of course. So let's do that first. We've got dc by dt. Now, I'm going to have a look at this, and I am going to make sure I understand what I am seeing here. I have got the derivative of this expression here plus this number here. Ultimately, for a rate of change or a derivative, I know that if I'm adding a constant value, that's going to disappear when I look at the derivative. So that's fine. I can effectively just ignore that when I'm working out the rate of change. If that was 2t there, for example, I'd be working out the derivative of this, and then I'd be going plus the derivative of 2t, which would be 2, right? But it just says 2, so I don't have to worry about it. But keep that in mind. This is just, at first blush, this is going to be the derivative of two things that have been added together, but this will disappear. Now I can look at this and I can see I've got two parts here that have been multiplied together. So I know I'm going to be using my product rule. So I follow my product rule nice and clearly, just using my usual method. U equals t over 4 minus 1. Therefore, U dash is equal to 1/4. And the minus 1, of course, goes to nothing. Quite a few people, when I was looking at this in class, didn't understand the idea that t over 4 is the same as 1/4 multiplied by t. Please be better at pulling out a coefficient like that. This needs to be like an automatic thought process for you to be able to pull out that 1/4. And then we've got v is equal to e to the power of t over 2. I might just even put that a little bit further over, so it's I'll make a quarter look a bit better. So I'll put a quarter so it's in that line, and then I'll be able to put e to the power of t over 2. Now, just be mindful that if e didn't have a power of t there somewhere, a variable as part of the power, it would just be a number. But because it's got a t there, I now know that that's going to be a power there. Now, we know the derivative of e is just e, or to be more precise, the derivative of e to the is e to the, as long as we've got some sort of variable there, like I was saying a second ago. So it's going to be e to the t over 2, like so. But then we need to consider that the chain rule still operates within the context of this little mini derivative that we're trying to work out. And the derivative of of t over 2, similar logic as this, is 1/2. So I'm going to squish in a 1/2 there, and there's my derivative v dash. Then, as you know, we look at the inside and add it to the outside here. So the inside is going to be 1/4 multiplied by e to the t over 2. Just making sure I've got it right. Plus, because that's how the product rule works, the outside, which is 1/2 e to the t over 2. I'm just looking ahead all the time. I'm not going to put this first and then this second, because this is a bit more of a complex expression. This is a compound simple expression, just things multiply together. This has two parts to it. So I'm going to put that second Just always thinking ahead a little bit so that I'm writing it in a way which is most efficient. So that's t over 4 minus 1. Okay, so there's my product rule done. And at this stage, I've done the derivative. I could just substitute in t equals 0 because that's what initial means. But I'm looking ahead and I can see there are different parts as well to this question. So I'm thinking, I can see that there's more parts to it. I might do a bit of simplification first, or in this case, bringing out some common factors. And genuinely, I don't really know, I can't remember, even though I wrote this problem, I don't really know how much factorization is useful. But I can see there's an e to the power of t over 2. That's definitely worth taking out. And then I've got this quarter and this half, and I'm just trying to figure out whether it would be useful to take any number out with it. But how about I just take that out to start with? So e to the t over 2 outside of a quarter plus a half outside of t over 4 minus 1. And I might even just simplify that a little bit more, because I can see, just looking ahead, there's some simplifications I can make. So a half times t over 4, I'm just going to expand the brackets there, is going to be t over 8, and a half times minus 1 is minus a half. And then I've got e to the t over 2. A quarter minus a half is minus a quarter, so I've got t over 8 minus a half. Maybe I should factorize this more. I'm not sure, but I'm just going to leave that there. And of course, I just made a mistake then. It should be minus a quarter. Okay, I'll leave it there, I think. And now I'm going to solve for 0. So at t equals 0, okay, so that's what we've been asked to do for the initial investment. I've got dc by dt is equal to e to the power of 0, because 0 over 2 is 0, and e to the power of 0 is 1, so that's fine. And then I've got 0 over 8 minus 1 quarter. Okay, that's fine. So the 0 over 8 is going to be 0. So I've got negative a quarter times 1, so that's going to be equal to negative a quarter. And the rate, of course, is millions of dollars per year. Okay, to summarize, just in your head, I suppose, I wouldn't write this down, but what that means is that at the time of the initial investment, the company will be losing $250,000, so 250 grand per year at the time of the initial investment. So it's losing money. And the reason why it's worth just making sense of it is because when we get to part B, that will make more sense of that. When does the company stop losing capital? And then you can go, oh, okay, I see. It's losing at the moment. When does it stop losing capital? Now, you don't know what this function looks like. There's an e to the power of there, but there's also t over 4 minus 1. You could have a bit of a guess at it. Of course, if this was in the calculator section, you could actually graph it to see what's going on. But you know that whatever's happening, it's sort of doing this at least for part of it. And then at some point, it's going to do this kind of thing. Maybe it's like this, who knows? But you can sort of see that it's going to be decreasing its capital. Then it's going to stop losing capital, because it says, when does the company stop losing capital? It's not saying, will it? So it's going to be stopping. And then obviously, if it's changing direction, so it's gaining capital, we clearly must have a turning point. So that's the thing to get to. There must be a turning point for this question to make sense. So we need to find that turning point. And how do we find a turning point? We set the derivative equal to 0 and solve. So I'm going to take the problem, dc by dt, from this point here, you know, the one where I just factorized it a bit, where it's sort of at its neatest, and then go, so that's t to the power, t over 8 minus a quarter, like so, and that has to be equal to 0 for that change in for the point of change from loss to gain. Okay, so that's cool. Where we go from there is, because I've already got it in product form, believe it or not, we can just go straight to t over 8 minus a quarter is equal to 0, as e to the power of t over 2 is never equal to 0. We know that. There's no number that we can put in for t to get e to the power of equal to 0. So I'm just using the null factor law, right? Which I'm now going to solve quite handily. So we've got t over 8 equals 1/4. Multiply both sides by 8, and I'll get t is equal to 2, i.e. in 2 years' time. Okay, so after 2 years, they'll stop losing money effectively, and they'll start gaining money, start gaining capital. Okay, cool. How long before they have doubled their capital from the initial investment? Alrighty, so doubled their capital. What does doubling mean? We know what doubling means. From the initial investment, oh, hang on, what did it say? The initial investment was $1 million. So what are we saying is how long? What is t? When c is equal to 2. Okay? Now, is that asking for a rate? No, it's not asking for a rate. So we don't have to use the rate. We simply need to use the formula. So we go c is equal to, I'm sorry for continuing to do scrollies, back to the initial formula, t over 4 minus 1. So c is equal to t over 4 minus 1 multiplied by e to the power of t over 2 plus 2, and that has to equal 2. Okay? Subtract 2 from both sides, and we get, t over 4 minus 1 e to the power of t over 2 is equal to 0. Oh, that's nice, isn't it? It's kind of a very similar logic to part B, in that in part C here, then, we can say t over 4 minus 1 must equal 0, just null factor law again, as e to the power of t over 2 cannot be equal to 0. So therefore, t over 4 is equal to 1, and t is equal to 4, i.e. they will be doubling their investment in 4 years' time. What is the rate of growth at that time? Well, good news. We've just worked out t. We have a formula for the rate of growth, the gradient formula. We just need to substitute 4 for t. So dc by dt is equal to, there it is there, e to the power of t over 2. Now, I'd personally just go straight into putting in my value of 4 here. But I'm just going to, because it's on a separate page, I'm just going to put it down again so it's easy enough to see. T over 8 minus 1/4. Is that what it was? Yep. And then at t equals 4, you would have e to the power of 4 over 2, which is 2, over 4 over 8, which is a half, minus 1/4, like so. So that will give us a half minus 1/4, which is equal to 1/4. So we've got 1/4 e squared. That is the rate of growth. That's millions of dollars per year, like so. Okay, now, if that's all you could do if this was a non-calculator question, of course, you don't know what, you certainly couldn't work that out with any more precision. That's the exact answer. If this was in a non-calc section, I'd be tempted to convert that into a decimal so that you can, have a bit more of a how many millions of dollars per year is it at that point kind of thing. It makes more sense in the context. I'll just see if I can grab a calculator quickly. And we've got 1/4, which is 0.25. 0. Oh, man, I don't use this often enough. Can't even find the point. Where's it gone? Wow. It is clear. This is good telly, isn't it? Okay, 0.25 multiplied by e to the, there we go, e to the power of 2 equals 0.412, so 1/4 of e to the power of 2. I think that sounds about right. So you could then write down, about the rate is you're gaining about $412,000 per year at that point, if my calculator's worked right. Like I said, this is pretty organic what I'm doing here, and I just used a calculator I don't normally use on my iPad, so, you know, I can't quite figure out whether that would be right. It feels about right, though. It's going to be a quarter of 1.2 squared. Feels about right. Okay, what is the average rate of growth over the same period of time from the initial investment? Over the same period of time from the initial investment. So that effectively means over the same period of time, that means up to 4 years from the initial investment would be from year zero. So what we need to do is determine that average rate of growth. And we do as following. Average is equal to, we just use our straight line gradient formula for that. At 4 years, we know the investment was 2 million. At 0 years, we know the investment was 1. I should say the capital was 2 million, and then it was 1 million at the start, all over 4 minus 0. Okay, 4 years to 0 years, 2 million to 1. So that's 2 minus 1 is 1 over 4. So the average is $250,000. So 250 grand. Millions of dollars per year. Notice I'm being really careful to put my rates in all the time. You could, you could write $250,000 per year. That would be appropriate as well, because we know that we often put dollars in front of the number symbol. But what I've written there, I think, would be absolutely reasonable because it does give you the right context, I think. Okay, anyway, so that's basically it. So it kind of looks more complicated, but it's not really. And then it's saying which rate of growth gives a more accurate picture of the company's performance, give reason to support your answer. So this is kind of like an analysis question. They're usually worth maybe 1 or 2 marks in the actual section. And look, you could argue both ways. I think I might just verbally say it rather than writing it down because it's probably a bit faster. You could, for example, say that $250,000, the average is a more accurate picture of the company's performance because it demonstrates what's happening, which is an overall growth of $250,000 per year. So it kind of ignores the fact that we're going to have some expenses to start with, and we're going to increase our growth later. So the average sort of tells us overall over the 4 years we did grow. Okay. You could argue that because this is an exponential function, effectively, I know it's not a pure one, but an exponential function, you could argue that the average actually undersells how the company will be projecting into the future. That sure, on average, it's $250,000 per year, but right now it's higher than that. It's 1/4 multiplied by E squared. The more I think about it, the worse I think that number was. It's going to be 1.2 multiplied by 1.2 multiplied by 0.25. Oh, maybe it was right. Yeah, 0.36. So it's about 360 grand per year at the moment. I did 1.2 instead of 2. It doesn't matter. 2.7 is what I should have done. Sorry. I'll do it again because that's really annoying. 2.7 multiplied by 2.7 multiplied by 0.25 is equal to, so it's actually much more than I was saying before. It's about $1.8 million per year is the growth rate there. And you can say, because it's an exponential function, this is a true reflection of how the company is performing right now after some expected initial losses due to starting up the company. So again, what you're looking for there in that what the marker is looking for is not a right or wrong answer, but a well-justified answer. And of course, you can make some really spurious claims, and therefore you won't get any marks on them because they're not reasonable. But anything you write down which is pretty reasonable would be accepted and you'd get marks for. Okay, that is where I will leave this one. Hopefully that's good enough. If there's any questions about any parts, please don't hesitate to ask.